Hello, everyone. As promised, I would like to share with you a walkthrough about how to get all the right answers on the in-class assignment for number 7. This says 9:30 at the top. The first page was the same for both sections. The last page was different, so I will switch over to the 11:30 version for the 11:30. I'm sorry, the 11 o'clock folk. Um, First, with the yes or no questions here. On number one, the presupposition that I laid down was that you have rejected the null hypothesis. That's the one thing that you know is true. What does it mean to reject the null hypothesis? Well, basically, if you're taking this as the model, then the fact that you rejected the null hypothesis means that you have gotten a result, your statistic for analysis has fallen on this side of the critical value. Whether or not you accept or reject the null has nothing to do with which distribution you're drawing from. It has to do with whether your answer was on one side or the other of the critical value. So you rejected the null hypothesis, which means that you're over here. Could you have made a type 2 error? Absolutely not. This red area represents type 2 error. That is the probability that you will fail to reject the null hypothesis if you're drawing from an alternative hypothesis curve. Since you didn't reject the null hypothesis, you couldn't possibly have made a type 2 error. Could you have made a type 1 error? Absolutely. If you got a result over here, but you were drawing from the null hypothesis curve, then you've made a type 1 error. So that's certainly possible. Okay, number two, you have failed to reject the null. That means that you are drawing a result from this side of the critical value. Could that have been a type 2 error? Yes, type 2 error exists on this side of the critical value. If you were drawing from the alternative hypothesis curve, then that result would have been a type 2 error. Could you have made a type 1 error? No. Type 1 error involves rejecting the null. If you fail to reject the null, then you can't possibly have made a type 1 error. Now, here's the number three, a different kind of a weird assumption that we don't usually get to make in real life, but I'm setting this up for educational purposes. Assume that the null hypothesis is in fact true, which means that you are drawing a result from this distribution right here, the one on the left. What is the probability that you'll make a type 2 error? None. It's impossible. You can't make a type 2 error no matter what you do if the null hypothesis is true, because type 2 error means failing to reject the null if the alternative is true. So if I've just told you that the alternative isn't true, you can't possibly make that error. What is the probability that you'll make a type 1 error? Well, that's what alpha is. If you are under the null hypothesis curve, there is an alpha probability that you'll reject the null anyway, um, and that's the green area. Alpha is determined before the fact. We're usually comfortable with a 5% probability of that happening. Assume that a specific alternative hypothesis is in fact true. What I'm telling you in number 4 is that we will be drawing a value from the alternative hypothesis curve here somewhere. What is the probability that you make a type 2 error? Beta is what that is. Beta is the probability that if you're drawing from an alternative hypothesis curve that you will nevertheless fail to reject the null. That's the definition of beta. The probability that you make a type 1 error, it can happen. If you reject the null under these circumstances, you've done the right thing. It's not an error at all. So a type 1 error means that you're drawing from the null hypothesis curve. Since you're not, you can't make a type 1 error. What's the probability that you'll reject the null hypothesis? That's power. That's 1 minus beta. So we're in this curve over here. I'm looking for the probability, which is the area under the curve, associated with being on this side of the critical value. That is 1 minus beta right there. Okay, number 6 and number 7, you decide to increase your alpha level from 0.01 to 0.05. What effect does this have on power? This will increase power. Take a look. Here is the line that is the critical value. That critical value is there because of the size of alpha. If I expanded alpha, if I made alpha bigger, if I made it push the critical error, it would push the critical value, it would push the critical value this way into the red. That would make the blue area bigger, which means that it would increase power. Group A runs an experiment and gets a standard error of 4.35. Group B runs the same experiment and gets identical results, except their standard error is 5.13. Which group will have more power? The smaller your standard error, the greater your power. the smaller standard error would mean that the same distance between these two peaks would now create greater separation between them if the error was smaller. All the null results would stick closely to mu sub null, and all the alternative results would stick closer to mu sub 1, which means that more of this curve, a greater proportion of this curve, would end up falling on this side of the critical value. Okay, at this point, we'll be moving on to page 2. Okay, walking through the 11 o'clock version of the back of the page. What I've given you is that there are two possibilities here. The first is the null and the second is the alternative. I'm going to start with the alternative because that kind of defines what the null is going to be. The alternative hypothesis is that corner lots, who I'm going to call population 1, get 4 more HOA complaints per year. That means if you subtracted the actual average of corner lot complaints from the actual average of non-corner lot complaints, you would get an answer of 4. It doesn't matter how many they get in general. It doesn't matter what the grand total is. The only thing that we're looking for here with a hypothesis test is the difference. And the alternative hypothesis is that the difference is 4. Now to the null hypothesis. If the corner lots and the regular lots get the same number of complaints, then the null hypothesis is true, but also covering every possibility in favor of non-corner lots having more is covered under the null hypothesis. So that's where we get our two distributions here. The first distribution here on the left is going to be the one where the two populations are exactly the same, which means that typically when you take a sample from one and you take a sample from the other and you subtract the two of them, you'll get an answer that is 0 or close to 0 because there wasn't any actual difference to be observed. The other distribution here is one where when you take a sample of corner lots and you take a sample of non-corner lots and you subtract the mean of the two samples, you'll typically get a result that's somewhere around 4, plus or minus sampling error. How much sampling error? Well, I gave that to you as well. The standard error is 1.5 complaints. I've also told you to assume that alpha is 0.05, and I've told you to assume that the sampling distributions are normal. That is a cheat. That is not a real assumption that we would use. What we would do if this was something that we were doing by the book would be to take up the number of people in the first sample, add it to the number of people in the second sample, and subtract 2 to get degrees of freedom, and then consult a t-table for those degrees of freedom. But as we'll see later on, it's not possible to use a t-table because we need all of the fine-grained values that are available on a z-table. So in order to use a z-table, we have to assume that they are normal. All right. So using all that information, I've asked you to give me a numerical value for power. What I'm looking for when it comes to power is this blue area here, all the way down to the corner and then all the way out to the end. What is the blue area? Which is to say, what is the area under the alternative hypothesis curve that falls on the reject side of the critical value? What we're going to find here is that the alternative hypothesis curve that falls on the correct side of the critical value is actually made up of 2 chunks. This chunk right here, which is just 0.5, half the curve. No problem, that's easy. The other chunk is right here, between the middle of the sampling distribution and the critical value. So we need to know how many standard deviations that is so that we can go to the z-table and figure out what area is associated with that number of standard deviations away from the middle. In order to do that, what we're going to do is figure out how many standard deviations are between the middle of the 2 distributions, figure out how many standard deviations are between the middle of this distribution and the critical value, and then subtract that number from the big number to get the number of standard deviations here. Take that to the z-table to get the area right here. Getting that area from a random value for the number of standard deviations is something that the t-table won't do, so we couldn't use it. This might be somewhat confusing for you, but what I want to point out is that what we're not doing is figuring out beta and then subtracting that from 1. Figuring out beta is too much of a hassle. In fact, we'd have to figure out power first in order to get beta. So we're going to do it this way by adding up these 2 areas. I'm going to work it through once one-tailed, which is kind of what I intended. But if you didn't do it one-tailed and you did it instead two-tailed, that's really not on you. That's fine. I'm accepting both ways of doing it as valid and correct. So in both cases, though, the number of standard errors that separate the middle of this distribution from the middle of this distribution is 4 complaints divided by 1.5 complaint per standard error. That means 2 2/3 standard errors separate this from this. Okay, 4 divided by the standard error is 2 2/3, 2.667. If you were doing this one tail, you could go to the z-table and figure out how many of those standard errors the critical value is from the middle of the null distribution by figuring out that if alpha here is 0.05 and all of this is half the curve, that means 0.45 of the curve is here in the middle associated with some number of standard deviations. If you take 0.45 into the z-table and look it up, you get 1.65. 1.65 is the number of standard deviations that are associated with a one-tailed t-test with an alpha of 0.05. So you have 2 2/3 standard deviations between these two middles. You have 1.65 standard deviations between the middle and the critical value. And now you can figure out how many standard deviations are between the critical value here in the middle of the alternative curve. That's simply 2.23 minus 1.65. That gives us between here and here 1.1066666 or 1.02 standard errors. With that information, we can go look up 1.02 in the z-table and figure out what area is associated with that right here. If you do that, z of a 1.02 taken to the t-table will give you 0.3461 of the curve. So that's this chunk right here. Add it to 0.05. I'm sorry, not 0.5. Add it to 0.5 right here, and together they come to 0.846. That is the actual power for the one-tailed version of these assumptions. If you did it two-tailed, the only thing that actually comes to make any difference is that instead of using 1.65, you're using 1.96. 1.96 is the familiar value we have from a two-tailed t-test. That means going 0.4750 in either direction, drawing a critical value right here, so that the last 2.5% is out here in the tail. That means going 1.96 standard deviations to that critical value. So 1.96 is that distance, meaning that the leftover distance to go 2.66 is actually 0.71. You are short less than 1 standard deviation. And if you go to 0.71 in the z-table and figure out an area associated with that, a z of 0.71 is associated with an area of 0.2611. So this area right here, where if you go 0.71 standard deviations to the left and look for the area, that is 0.2611. Add it to the entire other half of the curve, you get 0.7611. That is the answer up here for the power. Now, since power is technically a proportion, it's a proportion of area under a curve, the proper number of decimal places to include is 3. Not a big deal, but I've done it properly here. Notice, just for your edification, that a one-tailed test, if you give yourself the advantage of using a one-tailed test, you will, in fact, be able to increase your power, increase the probability that you'll find an effect. That's a little bit of a cheat, as I said before, but that's how the math works out. All right. See you again on Monday night / Tuesday morning for a talk on the next topic. We'll have another in-class assignment over that topic on Thursday. So see you soon.